So our final talk, unfortunately, the speaker couldn't be here, I think because of visa issues, but we will play a video. So it's accelerating Neural-ODE Inference on FPGAs with two-stage structured pruning and history-based step-size search. So this is a short paper, it's a 10-minute talk. The speaker is Li Kai. He's a postdoctoral fellow at the School of Integrated Circuits in Peking University in China. His research interests focus on neural network acceleration and model quantization based on memristors.
Hello everyone, my name is Li Kai. I'm a postdoctoral fellow of School of Integrated Circuits, Peking University. I'm very glad to have this opportunity to attend the conference. The topic of my presentation is about accelerating neural ordinary differential equation inference on FPGA. My presentation will include 4 parts. First, the motivations of our work. Second, the basics of Neural-ODE. Third, the algorithm and architecture we have proposed in the paper. Last, experiments and results about accelerating Neural-ODE inference. Okay, let's go to the first part. ResNet is built by adding residual connections. The left figure shows a typical ResNet structure with convolutional layer, batch normal layer, and ReLU layer. If we treat the blue block as a function f, the transfer function from layer k to layer k+1 is here. One may ask, why do we want to bring ODE to neural networks? The biggest motivation is that a convolutional ResNet can only inference discretely layer by layer, and the evolutional points are fixed. Extending it to a so-called Neural-ODE, the evolutional points become continuous, leading to better modeling performance. There is an integration process for Neural-ODE, and this integration requires a large number of iterations. Each iteration needs to find the optimal integration step. The integration process is shown in the middle figure with step size T. So finding the best step size in Neural-ODE is a challenge. More practically, state-of-the-art Neural-ODE is often used an advanced scheme like a Runge-Kutta integrator, where the integrator is shown on the left figure, on the right figure. Now let's go through the algorithm and architecture about Neural-ODE. Neural-ODE provides high-volume function approximation and good validated performance. RK integrator usually contains many orders. The right figure shows the 3-order RK integrator. The 3-order RK integrator consumes a lot of time in adjusting the step size. The contribution of our work, on the one hand, is to optimize the RK solution process. On the other hand, is to reduce the network size. The RK integrator is divided into 2 parts. One is the evolutional point, and the other is the step size trio. The evolutional point represents the integration process, and the step size trio represents the number of times to find optimal step size. Since Neural-ODE has to guarantee the final integration accuracy, it is a long process to find the best integration step size on inference time. First, we propose the Neural-ODE algorithm for optimizing the integration iterative process. The traditional search for the optimal integration step takes a lot of time. We use a history-based method to optimize the integration process. The left figure is the algorithm diagram, and the right figure is the flow diagram. In the flow diagram, we determine whether the current integration step size is accepted or not. And if it is, we increase the step size by a certain value. If it is not accepted, we revert to the original step size and then continue iterating over the new step size. By this method, we can save about 70% of the step size finding time. Next, we propose a two-stage pruning method. Our proposed two-stage structured pruning method consists of two main aspects. One is coarse-grained pruning, and the other is fine-grained pruning. First, we set a global sparsity threshold and then pruning all layers in the Neural-ODE according to this sparsity. The pruning process ensures that the network accuracy is not significantly degraded. Then we set the different sparsity threshold for each layer in the network, and then each layer is fine-grained pruned with guaranteed accuracy. The left figure shows a coarse-grained pruning process. We set maximum drop accuracy about 5%. As the level of sparsity increases, the network accuracy also decreases. The right figure shows the fine-grained pruning process. We set the maximum drop accuracy about 1%. The pruning level of each layer is also gradually increasing of the basis of coarse-grained sparsity. From pruning results, we can see that there is no significant decreases in network accuracy, and the number of the weight parameters is reduced by 36.5% on average, and the number of the feature map parameters is reduced by 33.75% on average. Furthermore, we designed the corresponding FPGA architecture to speed up the network inference FPGA. We analyze the parameter magnitudes of each layer in the Neural-ODE, and we count the number of the weights and feature maps in each layer. Second, according to the feature map of the Neural-ODE network, we propose the FPGA acceleration method. The FPGA architecture consists of three parts: a neural network loop, an RK loop, and a step loop. Neural network loop is responsible for the network inference part. RK loop is responsible for calculating the integration step, and the step loop is responsible for finding the best step size. For network pruning structure, we designed a convolution module on FPGA. Each convolution module contains multiple structured sparsity PE, named SPE. SPE is responsible for the weight pruning and activation function pruning of convolution. We specifically designed the FPGA-based pruning module. We counted the non-zero part of the network parameters and the dense part of the data separately, and use a mask to perform specific pruning. And we use a top-K algorithm to optimizing the pruning strengths. Okay, now we move to the last part of the experiment. First, we compare the energy consumption performance and inference speed performance between different works. Our experiments on the CIFAR 10-day set show that the inference speed of the network is 22.41 milliseconds for Neural-ODE single-layer inference time, and 164.04 milliseconds for the four-layer inference time. Next, we use three different bit quantization methods to quantify the model. We can see that the case of 12 bits, the model accuracy will still maintain 78.27%. In addition, it is worth noting that Neural-ODE can compress network scale by more than 50%. Finally, we compare the results of original Neural-ODE and our existing work in solving physical problems and image classification. We can see that our work and the original Neural-ODE have very similar integration trajectory. In the three-body equation and the Lochter-Vectory equation. At the same time, our work can still keep the accuracy losing within 3% in MNIST and CIFAR10 datasets. In the future, we will explore other applications of Neural-ODE on FPGA. That's all for my presentation. Thank you.